All right, let's do a real quick projectile motion problem here. That's got a basketball player doing a jump shot from somewhere on the court. It says a 6.5-foot tall basketball player can hold a basketball 2.5 feet over his head, jump 2 feet in the air, and shoot the basketball at 15 meters per second for a maximum range at an angle of 45 degrees. If the basketball hoop is 10 feet above the court, how far away from the basket can he make the shot? Okay, there's a lot of information in here, but really if you kind of write it all down, narrow it down, look at it on the picture, you see it's not as much as it seems. So let's start with his height. It says he's 6.5 feet tall. Next, we know that he can hold the basketball 2.5 feet over his head. And finally, we know that he can jump above the court by 2 feet. So you add all that together and you get the initial position of the ball as 11 feet. It's 11 feet above the ground at its initial position because we added all those numbers up and then bam, we got that. The problem also tells us that the basketball goal itself, the net, is 10 feet above the ground. So that would give us our final position. So now we know kind of our path of our projectile. We've got an initial and a final. And then we know that we're looking for delta x. How far away from the basket can this basketball player be to make the shot? All right, so the next thing that we're given is the initial velocity of the ball. It's shot out, of course, at this angle. And if it was a world without gravity, then it would actually just keep going like this forever and ever. But instead, gravity is going to start pulling it back down so it follows this parabolic trajectory. So we can go ahead and mark our velocity on there, an initial velocity, v0 of 15 meters per second. And we can then take that and break it into its components. We'll have a component in the x direction as well as a component in the y direction. So remember that the x is constant. We don't have to say vx naught, whereas the y velocity is changing due to gravity, so we do specify it as vy naught, initial velocity in the y direction. We also know that he's going to shoot this basketball at an angle of 45 degrees. So that's enough information for us to figure out what is the horizontal velocity and what is exactly the initial vertical velocity. Notice that the horizontal velocity is on the adjacent side of my triangle, with this being my angle, and my vertical, my vy naught, is on the opposite side. So if I wanted to solve for vx, which again is the adjacent side of the triangle with respect to this angle 45 degrees, it being adjacent and having the hypotenuse means I'm going to use the ca part of SOHCAHTOA. CAH means cosine of 45 degrees is equal to the adjacent side divided by the hypotenuse. And so if you wanted to solve that for Vx, you would get 15 meters per second times the cosine of 45 degrees, which is 10.6 meters per second. Of course, basic geometry will tell you that this is an isosceles triangle since it's 45 degrees and it's a 90-degree, right triangle here. Then this must also be 45 degrees, and so that means that these two sides of the triangle are equal. However, if you didn't know that, you could still solve for your Vy naught doing trig and 15 meters per second times the sine of 45, but again, that geometry is going to tell you that they're going to be exactly the same. Okay, and that's why this maximizes the range that can be made. It's getting the most out of your initial and vertical velocities at 45 degrees. Okay, so we started with our, first kind of two steps. Draw a picture, and in this case we annotated a picture. And then we asked ourselves, is there anything given at an angle? Well, yes, there is, and so we broke that into its components, resolved it into components. Next step, of course, is to make your table. So I'm going to start with the x direction, and I'm going to say anything to the right is positive, and then I'm just going to fill out all my variables, 6 variables in total, x naught x, vx naught vx, ax, and t. And of course, time is independent of direction, so I've shown it here in a different color from the rest of the x direction variables. We're saying that our ball is starting at the initial position. In this initial position, if my 0 is down here on the ground, then it is starting 11 feet above the ground. But that's my y position, of course. My x position, however, we're just saying that this is 0. And so it's 0 initially in the x, and then it's moving down this way. So my initial x is 0. My final x is, I have no idea, some delta x away. My initial velocity in the x, of course, is this 10.6. But recall that a horizontal velocity, as long as we neglect air resistance, which we are here, the horizontal velocity is constant. So it's going to be the exact same everywhere, which means Vx naught and Vx are the same, 10.6 meters per second. And again, that's because there is no acceleration. There's nothing to change that velocity. And then that leaves us with time, which we don't have. You need 4 things in the column to solve out. And this, even though it's technically 2 things here, it really only counts as 1. So we have 1, 2, 3 pieces of information, which is not yet enough in order to solve for time here. So now I'm going to look at the y direction. I'm going to say up is positive. I'll list out my variables for the y direction as well. All right, and then I'll go ahead and fill them out. Again, I'm going to say that I'm starting at the initial position 0. That initial position 0 is 11 feet above the ground, but I'm going to convert that into meters because I'm dealing with meters per second here. So 11 feet, and there's 3.3 feet in every meter. So here feet would cancel, leaves you with meters, and you get 3.33 meters per 11 feet. And then I'm going to convert the 10 feet, this 10 feet here, into meters as well. Again, 1 meter is 3.3 feet. So 10 divided by that 3.3, we get 3.03 meters for the height of the basketball net above the court. Okay, so now we can fill stuff in. Our initial position is 0. If on the ground, our initial position is 0. But we're going to start our ball right here at 3.33 meters, to 11 feet above 0. So our initial position in this case for our ball, for our projectile, is 3.33 meters. Okay, you could say it's 0 here. That's fine, but I'm just going to go and stick with this method. I just think it'll make a little bit more sense in the long run. Okay, and then the final position, y, is 10 feet above the ground, or 3.03 meters above the ground. The initial velocity in the y direction is what we calculated here is 10.6 meters per second. But remember, y changes due to gravity, so these are not the same like they were in the x direction. Then that leaves me with gravity, the acceleration due to gravity. I don't know the final velocity. It's not the same height. It's off by a foot, so I can't say that this is a negative 10.6. But back to the acceleration due to gravity in the y direction, of course, that's going to be 9.8 meters per second squared. And since it's down, it's a negative. And then finally, time. And remember, in these problems, time is the key. Time is what's going to tie my x into my y, or my y into my x. It's what's going to bring my 2 columns together. So let's just kind of quickly hash all that stuff back out. Recall everything that we just did, and then we're going to go ahead and start analyzing that information. So let's start by looking at option 1. With option 1, we could use the y direction to find time, because again, time is independent. If I can find time here, then I can plug it in up there, and ultimately that's what I'm going to need to solve for the range. However, let's go look at these equations real quickly. And remember, on the formula chart, it has a bunch of x's and the subscripts and stuff. There's no point in listing the same equation twice when you can just go in your head and replace every x with a y. So that would say Vy equals Vy naught plus Ayt, and so on and so forth. So I'm just putting y's in all of these. Now, looking at it, again, I'm only looking at my y direction variables. That's the only thing I want to look at plugging into here. I know that I have y naught. It's 3.33 meters, so I can check that off. I also know that y is 3.03 meters, so I can check those off. Vy naught is 10.6. I can check that off. Ay is negative 9.8 meters per second squared. I can check those off. And then time is ultimately what I'm looking for, so I'll check them off and circle them because that's what I want. But the problem is it's leaving me with these Vy's. I don't know those Vy's, and so I can't use those equations, which means there's only one equation that I could use if I wanted to find time with the y direction information, and that's that one equation that I could use. The thing is, if you were to use this, nothing's going to cancel out. You're going to end up being stuck using the quadratic formula, which is totally fine. In fact, in some ways, it's better to use the quadratic formula. But I'm going to do it a little differently this time than other problems we've done where we did use the quadratic formula. And all you have to do with this option number 2 is just solve for that missing final velocity first. You're going to solve for this Vy first, and then you'll go find time. So when you do that, you'll use this third equation. And so my third equation says Vy squared equals Vy naught squared plus 2a delta y. Remember, y final minus y initial is delta y. Okay, looking in there, nothing cancels out or goes to 0, but it's still relatively easy to solve. So Vy squared equals, Vy naught is 10.6 meters per second. Don't forget to square that, because it says Vy naught squared, plus 2 times the acceleration due to gravity is a negative 9.8 meters per second squared, and then times the y of 3.03 and the y naught of 3.33 meters. Okay, so now I'm just going to go ahead and punch all this stuff in the calculator straight out. 10.6 squared plus 2 times negative 9.8 times 3.03 minus 3.33, and you get 118.24 meters squared per second squared, which of course is Vy squared, so I still need to take the square root of both sides. Once I do, I'll have Vy, which is 10.9 meters per second. Tricky thing is, and listen very carefully, I can't get a negative value out of this. I took the square root of it, so it doesn't matter what it was not going to return a negative, even though it needs to be a negative value. Vy, final in this case, is going down as it approaches the basket. Therefore, over here, when I put 10.9 meters per second in my table, I need to write it as a negative. That is one of the trickiest parts of using this formula right here, is sometimes that is going to be a negative velocity, and when it is a negative velocity, it's up to you to remember that. It's not going to come out of the square root sign that way, so be careful. Okay, but now I can use an even simpler equation to find my time, and I can use that first equation, which says Vy equals Vy naught plus Ayt. In doing that, I'll plug in my numbers. So negative 10.9 meters per second equals 10.6 meters per second minus the 9.8 meters per second squared times time. Of course, I'll subtract 10.6 from both sides and then divide this by negative 9.8, and you'll get the time of 2.19 seconds. 2.19 seconds. So I'm just going to go ahead and write that in my table. Ultimately, I'm trying to solve for the range of my ball here. So I've got one step left. So I'm just going to go ahead and look back over here with my variables. Okay, so now what I'm going to do is I'm going to use my horizontal direction, my x direction, in order to find that range. We're not even paying attention to the y stuff anymore. Remember, I cannot plug anything from the y direction into equations for the x, so we'll just get rid of it. We don't need it. We use the y direction to find time, so we are done with it. Okay, so what we're going to do now is find range. Remember, range is horizontal displacement, which is delta x. Looking at our equations, we can use, there's really only one of these that's going to work for us, but let's go ahead and just look through them anyways. Checking what we've got, we have x naught. X naught is 0, so I can check that off. I can use that part of that equation. I can use that part of that equation. Ultimately, delta x is x minus x naught, so really it's x that I'm trying to find. That's going to be the answer to the problem. So I can check and circle that because that's, what I want. I know both the initial and final velocities are 10.6 meters per second, so I can check them off. And last, well, not last, also I know the horizontal acceleration, so I can check it off. And last, I know the time, so I can check it off. So now you'll see that every equation checks out. The problem is, like I said, there's really only one you can use. If you look at the top one, you're not going to be able to use it because it doesn't have x in it. How are you going to solve for x if you use that equation? However, if you do use this equation, it should tell you a true statement. It should come out accurate, and it will. It's going to tell you that 10.6 meters per second equals 10.6 meters per second plus 0. True, but not helpful. The last equation is going to do something very similar. Notice it does have x in it, so I could say maybe use it to find x. Problem is, that is going to end up being multiplied by 0 right there, which means it's not going to be helpful. This entire last term is going to go away because the acceleration in the horizontal direction is 0, which means what you're left with is this, Vx squared equals Vx naught squared, which tells me 10.6 meters per second squared equals 10.6 meters per second squared. Again, true but not helpful. It's the middle one that's going to work for us. So I'm going to go ahead and write that down. X equals x naught plus Vx naught multiplied by time plus half of Ax multiplied by time squared. And again, that entire last term goes away because A is 0. 1/2 times 0 is 0. 0 times t squared is 0. 0 times 5,296 is 0. 0 times infinity is 0. It doesn't matter. Anything times 0 is 0, so that whole term goes away. Same thing with little x naught here. He's also 0. It leaves you with the very simple equation that says x equals Vx naught multiplied by time. And that's it. X equals Vx naught multiplied by time. Bam. Just like that, and you get the final answer to the problem. 23.2 meters. And that's it. Apparently this dude shoots a basketball 23.2 meters down a court. I'd say that's a lucky shot.